Hello everyone. Have you ever wondered, if we throw a ball faster and faster, can we make it escape Earth forever? At low speed, it comes right back. Throw it harder, and it goes higher, but still returns. But imagine there's a magic speed where Earth's gravity just can't pull it back. That speed is called the escape speed. It's like playing tug-of-war with Earth. Most of the time, Earth wins. But if you pull fast enough, you break free once and for all. Let's see how physics defines this escape trick. Here's the key idea: conservation of energy. At Earth's surface, the total energy of the object is its kinetic energy plus its gravitational potential energy. That's 1/2 mv squared minus gmem over re. Now picture the object traveling to infinity. At infinity, potential energy is zero, and for the minimum escape case, kinetic energy is also zero. Total energy at infinity is zero. So, for an object to escape, its total starting energy must at least equal zero. That's the golden condition. Let's turn that into a formula. Set 1/2 mve squared minus gmem over re equal to 0. Cancel the mass m, and you get Ve equals the square root of 2gme divided by Re. We can also rewrite this using G equals gme divided by Re squared. That gives Ve equals square root of 2gre. And here's the fun twist: escape speed is independent of the mass you throw. Whether it's a cricket ball or a giant rocket, the magic number is the same. Time for numbers. Plug in G equals 9.8 meters per second squared and Earth's radius Re equals 6.37 times 10 to the power 6 meters. Ve equals square root of 2 multiplied by 9.8 multiplied by 6.37 times 10 to the power 6. That works out to around 11.2 kilometers per second. To put that in perspective, that's about 33 times the speed of sound. So, no matter how strong your arm is, you're not throwing a cricket ball into space anytime soon. That's a job for rockets. Now let's visit the moon. Because the moon is much smaller and lighter, its escape speed is only about 2.3 kilometers per second. That's less than 1/4 of Earth's. Here's why it matters: molecules of gases like oxygen or nitrogen move at high speeds. On the moon, many of these molecules easily exceed escape speed and drift away. That's why the moon has no atmosphere. So, escape speed doesn't just decide rocket launches, it decides whether a planet can even keep its air blanket. Let's challenge ourselves with a tougher case. Imagine two spheres, one with mass m, the other with 4m, and their centers 6 are apart. A projectile is launched from the smaller sphere toward the bigger one. Somewhere in between, there's a neutral point, a spot where the gravitational pulls cancel out. It lies 2 r away from the smaller sphere. To reach that point, the projectile must have just enough speed. By applying energy conservation, we find the required velocity is V equals square root of 2gm divided by 5r. Examples like this show how escape conditions change when more than one massive body is involved, just like real space travel between Earth and the Moon. So let's bring everything together. Escape speed is the minimum velocity needed to reach infinity with zero leftover speed. The formula is Ve equals square root of 2gm over r or square root of 2gr. It does not depend on the mass or direction of the object. For Earth, escape speed is about 11.2 kilometers per second. For the Moon, only 2.3 kilometers per second. This one concept explains why rockets need tremendous speeds, why the Moon has no atmosphere, and why gravity keeps some bodies bound while others drift away. So, the next time you watch a rocket launch, remember, The real race is against gravity, and the number to beat is 11.2 kilometers per second. That's all for today's session. See you in the next class with another exciting journey into the universe of physics.